On August 7, 1942, about 16,000 U.S. Marines landed on an island most of them couldn't even name, Guadalcanal. It was a hot, humid jungle in the Solomon Islands, and their mission seemed pretty simple. Take control of an airfield the Japanese were building. They did that in just a day and a half. And surprisingly, they didn't face much resistance. The Japanese forces pulled back into the jungle. Mission accomplished? Not even close. The airfield they captured wasn't even finished. It was just a rough strip of land, basically a dirt path. And this dirt wasn't easy to work with. In the tropical climate, it would bake solid under the hot sun and then turn into sticky mud after heavy rains. When dry, it felt like concrete. When wet, it was more like pudding. The Marines quickly realized they had a big problem. In Pacific Island warfare, it's not just about holding land. You need control of the skies. And without a working runway, you can't launch planes. The Japanese understood the importance of that runway, too. Just days after losing it, they started bombing the area constantly. The Marines named the airstrip Henderson Field, after a pilot who died at Midway. But the biggest threat wasn't the bombs. It was the mud. Every time it rained, the runway became useless. Their fighter planes and bombers, essential for defense, would sink into the soggy ground. Mechanics watched as planes slowly disappeared into the muck. One pilot tried to take off but just dug deep trenches without even getting off the ground. 20 minutes later, Japanese bombers arrived with nothing to stop them. Engineers tried every trick they knew. First, they used crushed coral from the beach, but rain washed it away. Then they tried laying down steel planks designed for building bridges. But in the tropical heat, the metal warped and bent. Even the machines used to flatten the ground got stuck in the mud. By mid-August, Henderson Field was only usable about 3 days a week. On the other days, without air support, the Marines were sitting ducks. Japanese ships could attack freely, and enemy troops could sneak in reinforcements during the night. The situation was clear. If they couldn't fix the runway fast, Guadalcanal would fall. And if that happened, the entire Pacific campaign could be pushed back a year or more. Back in Washington, the Army Corps of Engineers started getting urgent messages. We need a fix immediately. Luckily, they'd already been testing solutions to the soft ground runway problem, even before the war began. They had tried different ideas at airfields from swampy Louisiana to frozen Alaska, but none of the experiments had fully worked, and now the consequences of those failures were playing out in real time. The first real attempt was in early 1941. Engineers tried something called square mesh track, basically welded steel bars that looked like heavy-duty fencing. The idea was to spread out the weight of planes. But when they rolled a B-17 bomber across it, the mesh collapsed. The steel wasn't strong enough. They considered making the mesh thicker, but that made it so heavy it would need entire ships just to deliver enough for one runway. Next up, a British idea using burlap fabric soaked in asphalt. It had worked for temporary roads in North Africa, so American engineers tried it for aircraft. They rolled out huge sheets of jute fabric soaked in hot asphalt and tested it with fighter planes. The first few landings were fine, but by the 10th, the surface had ripped up and pieces got stuck in the plane's landing gear. That plan was scrapped. Then came the coral and gravel solution. It looked promising since it resembled the hard-packed natural ground found on many islands. In July 1941, engineers built test runways using crushed coral and volcanic rock, then rolled over it with steamrollers. It worked well until the rain hit. A heavy tropical downpour turned the whole runway into mush. The surface eroded so badly you could stand in the gullies it left behind. And once coral breaks down when wet, it can't be packed down again. You have to start from scratch. One method that came close to working was pierced steel planking, or PSP. Originally developed in the UK for roads, these were long steel plates with holes to cut weight and give grip. The U.S. started testing PSP in August 1941. The good part? It could be installed fast, like putting down roofing shingles. But in the tropical heat, the metal expanded and warped, creating sharp ridges that could wreck planes on landing. Pilots said touching down on it felt like hitting a washboard at high speed. By fall 1941, Engineers were out of ideas and out of time. Then came Pearl Harbor. Suddenly, fixing the runway issue wasn't just important. It was critical. The Army Corps of Engineers sent out an emergency request to American steel companies. They needed a surface that could be installed quickly, hold up to planes weighing 50,000 pounds, work on any ground type, and survive tropical heat, all while being light enough to ship across the ocean on crowded supply ships. Carnegie-Illinois Steel Corporation, based in Pittsburgh, got the job. Their lead engineer, James Marston, looked over all the past failures and saw the same mistake repeated. Everyone was trying to build a solid surface like concrete. His idea? Stop fighting the mud. Just float on top of it. He began sketching a design that didn't look like a road at all. It looked more like a flexible sheet of metal, something that could adapt to whatever surface it landed on. By February 1942, James Marston and his team had built a working prototype. It looked simple, a steel plank 10 feet long and 15 inches wide, but it was a breakthrough in design. Each plank was made from high-strength steel, just 3/16 of an inch thick. That made it strong enough to carry the weight of planes, but light enough, about 66 pounds, for 2 men to move into place without any machines. They punched rows of holes through every plank, creating a pattern that looked almost like a steel grater. But those holes weren't for looks. They served 3 key purposes. They cut the weight by around 30%, they let water drain instead of pooling, and they gave aircraft tires better grip. The real innovation, though, was in the edges. Marston's team spent months perfecting the sides, so that each plank could lock into the next without any tools. One side had a raised lip with a hook, the other had a groove to receive it. You'd lay one plank next to another, and the hook would slide right into the channel, holding tight just from the pressure. No bolts, no welding. The connection was strong enough to let a 50,000-pound aircraft roll across it without the planks separating. And because the whole thing had some give, the runway could adjust to uneven terrain without cracking. The short ends of the planks used a simple overlap. One slid under the next. That way, the surface was continuous, with no gaps large enough to snag a tire. The more weight pressed down on it, the tighter the planks locked together. In March 1942, the Army tested the system at Camp Claiborne, Louisiana, a spot picked on purpose because of its swampy, unstable soil. Engineers laid 1,200 square feet of the Marston planks right on top of the soft ground and rolled a fully loaded B-17 bomber across it. The mat flexed. You could actually see it move under the weight, but it didn't fail. Over 3 days, they ran 50 takeoffs and landings. There were surface scratches, but no major damage. When they checked underneath, the soil had compressed about 2 inches, but the pressure had been evenly spread across the mat. No cracks, no splitting. That was all the proof the military needed. They immediately ordered 60 million square feet. To understand why this design worked, you've got to look at how planes affect the ground when they land. It's not just about weight. It's about pressure. A B-25 bomber, fully loaded, weighs about 35,000 pounds. But that force gets focused through just a few landing gear tires, each tire pushing down on a few square feet of surface. That adds up to nearly 9,000 pounds per square foot. Soft ground can only hold about 300 pounds per square foot before it gives way. So the problem is obvious. The Marston Mat system solved this by spreading the weight out. When a wheel landed on one plank, that force didn't stay in one place. Thanks to the interlocking design, it spread across the neighboring planks, on both sides and front and back. That load-sharing effect meant that by the time the pressure reached the ground, it was down to about 90 pounds per square foot. Totally manageable, even for bad soil. Another key was flexibility. Concrete runways are stiff. They only work well on solid, stable foundations. On soft or shifting ground, they crack and fall apart. If just one part sinks a bit, water gets in, the crack grows, and the whole surface quickly deteriorates. But the Marston Mat wasn't rigid. Each plank could shift slightly, just tiny amounts, while staying locked into place. That made the entire runway act like a floating surface, adjusting to whatever was happening underneath without breaking. The holes in each plank also help with drainage. In the Pacific, where rain is constant, Water would simply run to the holes instead of pooling on top. That reduced the risk of hydroplaning. The holes were only about 2 inches wide, so tires still had plenty of grip on the solid metal parts. Tests at Wright Field in April 1942 showed water drain off a Marston Mat surface 6 times faster than off a solid one. There was another unexpected benefit, too: quick repairs. When bombs damaged a concrete runway, fixing it took heavy equipment, new materials, and several days. With a Marston Mat, if a bomb hit, crews could just remove the damaged planks, slide in new ones, and get back in business. At Henderson Field, engineers timed one of these repairs. They replaced a 20-foot stretch of mat in under 40 minutes, not counting the time needed to fill the crater itself. Because no special skills or tools were needed, training was quick. Workers just needed to follow the pattern and move fast. On August 17, 1942, the first shipment of Marston Mat reached Guadalcanal. The cargo ships delivering had to sneak past Japanese submarines to get there. The Naval Construction Battalions, the Seabees, unloaded 36 tons of steel planking while under enemy fire. Japanese Zero fighters were strafing the beaches as they worked. Most of these guys had never seen Marston Mat before. Just months earlier, they were civilian workers, carpenters, welders, machine operators, building highways and bridges across the U.S. Now, they were in a war zone, trying to build a runway from scratch while bullets were flying. The first thing the Seabees noticed: those 66-pound planks didn't feel too bad, until you had to carry them for hundreds of yards in 100-degree heat and suffocating humidity. They quickly built a system out of pure necessity. 2-man teams hauled planks from the stockpile to the edge of the runway. A third person lined up each piece, making sure the edges locked in correctly. The first row was easy, just laying planks side by side on clear ground. But after that, every new row had a hook into the one before it. They figured out the trick: tilt the new plank, slide the hook edge under the existing one, and drop it into place. When it was locked in, you'd hear a sharp metallic click. The sound of success. They worked fast, but never for long. Japanese bombers attacked Henderson Field nearly every day, sometimes twice. The Seabees kept watch for scout planes. If one flew over, they knew bombers were an hour behind. When the alarm sounded, they dropped everything and ran for cover. After the bombs fell, and a few minutes passed for any unexploded ones to go off, they got right back to work. If a bomb hit a section they'd already laid, they removed and replaced the damaged planks. If it hit a section they hadn't gotten to, they filled the crater with coral and kept going right over it. 3 days after the first load of Marston Mat landed on Guadalcanal, a 200 by 75-foot section of runway was up and running. It wasn't full length yet. Henderson Field needed 5,000 feet for bombers, but it was enough to get fighter planes in the air. On August 20th, 19 Wildcat fighters and 12 Dauntless dive bombers landed. These were the first planes of VMF 223 and VMSB 232, which would become known as the Cactus Air Force, named after Guadalcanal's radio call sign. These pilots were landing on steel that hadn't even been on the island 72 hours earlier. They said it felt different from concrete or dirt, softer, with a little give, like a trampoline. Some said that slight flex actually helped. Hard landings weren't as rough because the mat absorbed part of the impact. By September 5th, Henderson Field had a full runway made of Marston Mat, 5,200 feet long, 150 feet wide. It had taken just 19 days to finish, even with constant bombing and artillery. A traditional concrete runway would have taken at least 3 months, and that's under perfect conditions, which Guadalcanal definitely wasn't. Guadalcanal proved the system worked, but what happened next showed how powerful it really was. By early 1943, the U.S. began its island-hopping strategy, moving across the Pacific toward Japan. Every island needed an airstrip, fast. The Japanese plan was to slow U.S. forces down with heavily defended island fortresses. Marston Mat turned months of runway work into days. February 1943, Russell Islands. Marines landed expecting a fight, but the Japanese had already left. Within 60 hours of the first boots on the beach, the Seabees had built a working fighter strip with Marston Mat. When Admiral William Halsey arrived, he was so shocked at the speed. He asked the commander if they had started construction before the island was secured. They hadn't. They had just become that efficient. That runway gave air support for the next mission in the Solomon Islands, turning what would have been weeks of exposure into just days. August 1943, Munda Point, New Georgia. This time, the Japanese were still there. They were dug in above the Airfields site, and the Seabees laid planks under live fire. They came up with a plan. Half the team installed matting, while the other half provided cover with rifles and machine guns. 14 men were killed, 47 were wounded, but the runway was operational in 11 days. Corsair fighters were flying out of Munda, while enemy snipers were still being cleared from the edges. November 1943, Bougainville. Here, the military tried something new. Pre-assembled runway panels. Instead of laying each plank by hand, engineers in Australia started building 50 by 15-foot sections in advance. These massive panels were loaded onto landing ships and dropped directly onto prepared ground by crane. What once took 2 weeks was done in 4 days. By December, Bougainville had 3 complete Marston Mat runways arranged in a triangle, allowing planes to land or take off in any wind condition. The numbers tell the rest of the story. In 1942, the U.S. made 8 million square feet of Marston Mat. In 1943, that number jumped to 40 million. By 1944, they were making 60 million square feet a year, enough to build a runway from New York to Philadelphia. So much steel went into runway matting that it caused shortage. Tank production was briefly slowed because steel mills were too busy making Marston Mat. January 1945, Lingayen Gulf, Philippines. Engineers started using Marston Mat in new ways. They laid it on the beach to make instant roads and piers for supply trucks. It worked just as well for wheels as it did for planes. Before, trucks would get stuck in sand. Now, they could drive straight from the landing craft to the supply zones. February 1945, Iwo Jima. This was the most famous use of Marston Mat, though most people don't realize it. Iwo Jima was made of loose volcanic ash, like building on powdered sugar. Concrete wouldn't set. You couldn't pack the ground. Nothing worked, except Marston Mat. Seabees laid it down on all 3 airstrips while the battle for Mount Suribachi was still raging in the background. When the war ended in August 1945, the military thought Marston Mat was finished. With peace, there'd be time to build permanent runways again. The leftover matting was stockpiled across the Pacific, tons of it sitting unused, ready to be scrapped or sold off. Then June 25, 1950, North Korea invaded South Korea. The U.S. rushed to gain air superiority in a place with barely any infrastructure. Those old stockpiles of Marston Mat were pulled out of storage. Korea wasn't the Pacific. The terrain was mountainous, with frozen ground in winter. But even in the brutal cold, Marston Mat still worked. Steel gets brittle in low temps, but the interlocking design held strong. What made Marston Mat work on soft ground also made it perfect for frozen terrain. When the soil expanded in freezing temperatures, the mat flexed upward. When the ground thawed and sank, it flexed right back. No cracking, no separation. In September 1950, Kimpo Airfield near Seoul became the test. The runway had been destroyed by retreating North Korean forces. U.S. engineers laid Marston Mat directly over the broken concrete. Within 72 hours, the runway was ready. F-86 Sabres were flying missions from Kimpo, while teams were still clearing rubble on the other end. By the end of the Korean War, 38 airfields were using Marston Mat. It got a new official name, PSP, Pierced Steel Planking. The name changed, but the product stayed the same. Then came Vietnam. It was 1965, and that same mat, some of it literally from Guadalcanal, was still being used. At airfields like Da Nang and Bien Hoa, engineers laid it down to expand runways and build landing pads for helicopters. The climate in Vietnam, monsoons, extreme heat, acidic soil, was almost identical to the Pacific Islands. The mat performed just as well as it did in 1942. But after Vietnam, Marston Mat took an unexpected turn into civilian life. Oil companies in Alaska and Canada started using it to build temporary roads and platforms over permafrost without damaging the fragile ground. The same load distribution that stopped bombers from sinking into jungle mud now kept heavy trucks from melting the Arctic floor. Even environmental groups supported it. Unlike permanent gravel roads, the mat could be removed after drilling. Once gone, the tundra could heal. Then in January 2010, disaster struck Haiti. A 7.0 earthquake wrecked most of Port-au-Prince. The main airport runway survived, but the rest of the infrastructure collapsed. Relief flights backed up with nowhere to go. Within 48 hours, the U.S. military flew in pallets of Marston Mat and laid it across damaged taxiways and parking areas. Planes full of food and medical supplies could now land, unload, and clear out quickly. A wartime invention meant for the Pacific was now saving lives in a humanitarian crisis. Today, military forces still use it. It's called AM2 matting now, short for aluminum membrane version 2. The steel's been replaced with lighter aluminum alloys, but the idea is the same. Interlocking planks, perforated surfaces, flexible but tough. The British Royal Air Force still uses it. NATO forces use it in Afghanistan to expand the air base at Bagram. It's used after hurricanes, typhoons, floods, anytime fast infrastructure is needed in a disaster zone. And the original mats? They're still around. Some have been turned into footpaths, fences, or bridge decks. On some Pacific islands, you can still find sections from World War II, worn, rusted, but still holding strong after 80 years. We often hear that wars are won with tanks, planes, and ships. That's what shows up in the movies and textbooks. But real victories often come from behind the scenes, from the tools that make everything else possible. Marston Mat was one of those tools. Before it existed, taking an island meant months of construction before it could be used. You'd seize the ground, then wait for surveys, wait for concrete, wait for cure time. During that whole period, your forces were exposed, and the island itself wasn't helping you yet. The Japanese counted on that delay. Their whole strategy was built on slowing the U.S. down, forcing Americans to bleed for every inch, and then tying them up in long construction timelines afterward. They expected progress to crawl. Marston Mat shattered that plan. Now, the U.S. could land on an island and have planes flying off it in a matter of days. Suddenly, places that once seemed like a logistical nightmare became stepping stones in the march toward Japan. That's how the Central Pacific Campaign, Tarawa, Kwajalein, Saipan, succeeded. With Marston Mat, newly captured islands could support the next attack right away. The result? Momentum never stopped. By the end of 1944, the U.S. had built over 300 airfields across the Pacific. Around 220 of those used Marston Mat, fully or in part. Without it, maybe a third would have been possible, and they would have taken 3 times as long. That would have meant fewer bases, longer flights, weaker air cover, and a slower path to victory. Think about the bombing campaign over Japan. The B. 29 raids that helped force surrender were launched from Saipan, Tinian, and Guam, captured in mid-1944. Just 5 months later, those islands were launching full-scale bombing missions against Tokyo. That timeline only worked because Marston Mat runways were finished in weeks, not months. If the military had to wait for concrete, those raids might not have started until mid-1945, changing everything about how the war ended. This wasn't about a new material or a revolutionary invention. Carnegie-Illinois simply asked better questions. How do you build strength without making it rigid? How do you make it light without making it weak? How do you make it so easy to use that exhausted troops can put together while under fire? The brilliance was in the simplicity. Strong, interlocking steel planks, holes that drain water, flexibility that bends but doesn't break. Historians often say the Pacific was a carrier war or a logistics war, and that's true. But beneath all that, it was also a war solving engineering challenges under impossible pressure. James Marston and his team may not have built weapons, but what they built saved lives and helped end the war sooner. They turned mud into runways. They turned islands into air bases. They turned the impossible into reality. and they did it with nothing more than steel, ingenuity, and a few well-placed holes.